Um, I think we should start. So I think you can hear me, guys. Can you hear me, please?
Yes, I can hear you.
Okay, thank you so much. Well, good afternoon, everyone. I hope you're doing well and safe. So I'm glad to moderate this session for today. I'm Jumana, a second year of transportation of hydrocarbon. So welcome, everyone. And thank you so much to joining us this session. And thank you so much, really. So let's start. Okay. An essential key to successful water flooding project is a well-planned and a well-executed program of surveillance and monitoring. This program should be tailored to address individual project or field because each water flood, will have a different characteristic. So to go deeper through the topic, we are pleased to host today Mr. Abdurahman Grada, Reservoir Engineer at Akakus Oil Operation Company, to present water flooding, monitoring, and surveillance, who kindly accepted our invitation to go through this interesting topic. So, our guest is a reservoir engineer with a 4-year experience at Akakus Oil Operation Company. He has been involved in the various projects such as water flooding project, whilst stimulation project, specifically acidizing in sandstone reservoir. He has been in the field development plan project for a multi-layered sandstone oil field. Mr. Grada has a master's degree of petroleum engineering from UPM Madrid, Spain in 2019. So guys, we will start. Please, if you have any question, just write it in the chat box and don't forget to mute your mic to don't bother other. Mr. Abdurrahman, can you hear me?
Yes, I can hear you.
Okay, the mic is totally yours. You can start.
Okay, thank you, Ms. Jumana, for the nice introduction. First of all, I'd like to thank you all for attending this webinar about, water flooding and surveillance, which is like the part of secondary recovery, as you will see later. And it's like an important stage in the life of the oil fields, to maintain the reservoir pressure and also to maintain the productivity of the reservoirs. So initially, the webinar provides tools and procedures that will include sort of prediction techniques to support in, surveillance of ongoing activities, and also aids in the process of entering an initial water flooding design for mature fields. Sometimes you work for mature fields and the water flooding project has been already designed, and now the main target of you is to monitor and how to optimize the process instead of initializing the project from scratch. Okay. Here we have the table of content. We will start the concept of water flooding, and then we will have why we need to invest our money to do water flooding. And then after that, we will quickly pass through the main stages of water flooding, that starts from the end of primary depletion until the end of the flood project. Then we will analyze the performance of water flooding from, starting from the field level. Then we will zoom in to the well or to the pattern level. Okay, and then we will have, starting talking about the well level. So as you may have noticed that at first, we will focus more on the theoretical approach of water flooding, and then we will have something like more interesting because we will have like real data and we will practice the how to perform or how to analyze the performance of water flooding in the different level as we will see. So as you may know that oil production can be separated into three main phases. We have the primary, secondary, and the tertiary, which we always known as enhanced oil recovery. So we have three main stages. The primary oil recovery is limited to the hydrocarbons that naturally rise to the surface, or in some situations that could be, we can use some useful artificial methods like ESP or electrical submersible pumps or gas lift to produce the fluid to the surface. So as we can see in the blue curve, that's the primary where we have, and depending on the reservoir pressure to produce the oil. But you should agree with me that with the time you'll keep producing, the pressure of the reservoir will be depleted. So we need to boost it up. We need to enhance it by introducing another source of energy. And here, what we call the secondary recovery. So the secondary recovery is an important stage in the life of any oil fields when the reservoir pressure, is reduced to a point where it's no longer effective to move hydrocarbons to the producing wells. In that case, we do either one of two things. The first one is water or gas. The second one is the gas injection to increase the reservoir pressure. So in the red area under the secondary recovery, you have two titles. The first one, gas injection, and the other called the water injection. The gas injection and water injection both, come under the secondary recovery. Today, I'm gonna talk about water injection, and maybe when you get the opportunity, of course, I will talk about the gas injection. It's really interesting. Okay, so after the secondary recovery, the question will be, after water flooding has been done, what should I do to increase the recovery? Okay, so that's, here we come to the green area, and we will say that we can add another thing, in addition to just water and gas injection. It might be, water with other chemicals inside. It might be polymer, it might be surfactant. It might be like water mixed with other additives to make, more recoverable oil. It might be heating that oil before producing it, or another techniques. It could be like using bacteria to remove or to produce oil. So these are the main stages of, any oil fields. Sometimes you need to start secondary recovery from the first days or from the first years or months, like from the oil field. That's actually depends on the natural drive mechanism that you have. Sometimes you don't have drive mechanism and you will start depleting very fast because you don't have sufficient energy to produce. So that's why we start early. Sometimes it took years to start implementing water flooding projects because we have like good aquifer and we have better conditions. So that's why we delay the process, because we have like late depletion periods. So this is a general framework of water flooding. What I've been saying is just water injection, but from this slide, there must be a difference between water injection and water flooding. So is there any difference between water flooding, or what is the main differences between water injection and water flooding? When I inject water into the aquifer, that's called water injection. It's really simple as this. So the water injection well, as you may notice, is much deeper than the water flooding well, because we go like deep inside to the water aquifer to, for example, to build up the reservoir pressure. However, in the water flooding, we inject water into the oil zone, like in the blue zone, as you see in the right side of this picture, to increase the sweeping efficiency. And that's in addition to the, pressure maintained. So if someone asks you which one is good for building the reservoir pressure, you would say that injection or water injection is good for restoring the pressure or building the reservoir pressure. And which one is good for sweeping the oil? Of course, you'd say water flooding is better for sweeping the oil. But at the end of the day, the injection and flooding, there are different applications, for and they are part of, secondary recoveries, but each one has got different or unique usage. So let us go deep about water flooding and what is exactly water flooding process and how does it work? Water flooding is a process of injecting water into the reservoir in order to, recover oil left in the pore space at the end of primary recovery. And the water is injected into the oil zone, that physically displacing the oil residing in the pore space and moving it towards the producer. So this is the main idea of water flooding. Usually, the production and injection wells are arranged in various schemes or patterns to achieve, efficient oil displacements by water. And these patterns, designed to accommodate different things, like they should accommodate the variations in the reservoir properties, and they should accommodate the variations in the fluid properties. And sometimes you can take into considerations the project life. You can take in considerations the project economic as well. So let's say you are a reservoir engineer, but you should have like the basic knowledge of what is economic. I mean, the basics of economics that led you to understand how these projects, like, are they viable or not, or should be helps you to make the right decision. Okay, so as a general overview, the water injection is injecting water into the aquifer, while flooding is injecting into the oil zone. Water injecting into the oil zone might be a bit of tricky, because you are injecting in the oil zone. You don't need to leave oil behind. So that brings us to the second slide. What are the main factors that we must consider before we start water flooding? Because we are dealing with an important layer. We are dealing with oil zone layer. So it's important to know what is what are the main factors that is important in my case. Of course, you need to know about the reservoir geometry. I mean, the shape of the reservoir. Is it like radial or spherical? Is it like a fold or an anticline? Is it a salt dome? So that's important to know, the geometry of the reservoir. Another thing you need to know about the oil properties. What is ABI? I mean, what's the water content, and what's the gas oil ratio, for example? You should know what's the viscosity of the oil and formation volume factor. And why do you need to know all the fluid properties? Of course, if you have like a high viscous oil, the just injecting water, I mean the pure water, might not be woken properly. Why? Because it's high viscous and it's sticky. I mean, it's really difficult to do the displacement process. So you might need to add like surfactant, or you might need to heat it up before you produce it. So that's why you need to understand the petrophysical or the fluid properties. Another thing you need to understand, which is really, really important, which is the reservoir lithology. We should be aware of any clay content, and of course the mineralogy of the reservoir section. For example, like if you have like too much clay content and the water attacks that shale content, so what do you think the shale will do? The shale will swell up and then closes, or at least reduces the permeability. So the injected water cannot, move any further. And actually, you don't want that happen. So if you have a clay content, try to avoid, just using water. Try to understand what are the mineralogy of that lithology, and then after that you can introduce the proper additives to that water to prevent that swelling. Okay. And also, if you have like any natural fractures, I mean, what will happen if you inject water in the natural fracture reservoir? Basically, it will escape like everywhere, and it's like, that's what we call, water fingering. I mean, the water takes the wrong path due to the heterogeneity, so I will not get the good sweeping for that oil. So the injected water will run like very fast, leaving the oil behind, unless we, as I told you, we inject like polymer with that water to make it like more viscous, to have better sweeping efficiency. And this is like an example where if you have like a fractured reservoir and the injected water goes everywhere, but it's not like covering very good efficiency, sweeping efficiency. But in this reservoir, what do you think the main problem? We have actually two main problems, and they are like the first enemies of of any water flooding project. We will start producing water in the early stages of water flooding, okay, and we will leave oil behind in you can see that water reached here, but there's some oil, a lot of oil is being left behind. So that's reducing the recovery. Instead of increasing the sweeping efficiency, you are reducing the recovery. And that's why you need to use, for example, polymer to improve the sweeping efficiency. And when I say sweeping, it's aerial, vertical, and volumetric sweeping efficiency. So you need to know very much about the lithology of that, of your reservoir. And also you need to know the rock properties. For example, you need to know the saturation. It has been said that if the saturation is less than 50%, so it's better to avoid water flooding. So understanding the petrophysical properties is quite essential as well. Another thing you need to understand from the very beginning, what's the drive mechanism? What's the natural drive mechanism? Do we have a strong aquifer? Do we have a weak aquifer that is not enough to maintain the reservoir pressure? We don't have an aquifer at all. So all these things will have, it should be taken into considerations before we start, because of course we need to inject water, but how much amount of water? I mean, do we have any other source of energy that may help the water flooding process or not? So all these things must be taken in considerations before start implementing water flooding project. Then we have like everything on this earth has pros and cons. I mean, there are some advantages and disadvantages of water flooding. But practically speaking, many complex enhanced recovery processes have been developed through years of experience. But water flooding is currently, most widely used fluid injection. And this is, responsible for a significant portion of oil being produced in the worldwide. For example, in Canada and USA, the water flooding projects account for more than half of the current oil production. So this is a huge percentage, isn't it? And actually, because of many advantages, as you can see here, we can pass through different advantages. The first one is general availability of water. The water is more available than any other fluids on this earth, which make it with a very, at least low cost relative to other injection fluids. It's, as I told you, the economics is really important before implementing the project, and the general availability of water makes it relatively lower cost than any other injection fluids. And also it's easy to inject water into the formation. For example, we don't need to have a certain pressure. And for example, in the gas injection, we will have a minimum miscibility pressure. We will have a certain pressure we should have in our reservoir before injecting gas. But we don't need to do that here in the water flooding. So that's make it much easier for the injection process. But before we inject water, you have to test the compatibility of the injected between injected water and the water that exists in the formation. If they're not compatible, they might introduce another problems, as we will see in the disadvantages. And the last one, which is the most important one, it has been proved that the high efficiency of water, by displacing oil, and this have been approved through many years of experience and development studies, and that's the beauty, and that's the most important thing in the water flooding. So an essential key to successful water flooding projects is two things. The well planned, there should be a good planning for the well, before implementing the water project. And the other thing is a well-run monitoring and surveillance after the water flooding is implemented or while water flooding is implemented. So this is a critical issue, and especially for poor quality or geologically complex reservoirs. As I told you, if you have highly fractured reservoirs or multi-layer system, that makes it, or heterogeneous reservoir, so that makes it a bit not an easy task to get. Like, but always push in your mind that even with the best of intentions, water flooding plans and expectations are usually based on a meager amount of data. And like a judge's approach is to do your best always under the under circumstances, and they and also you should be prepared to deal with any kind of surprises. Some they might be pleasant and you would be happy because of you have like good surprises, but other surprises might not be that pleasant. But always keep in your mind that surprises can provide useful information, like if you correct or if you interpret them correctly. So if you have interpreted your data correctly, you can suggest ways to steer the process towards the optimizing flooding project. So that's basically the advantages. And what are the main disadvantages that we have? Do we have disadvantages or not? In fact, yes, we have disadvantages. They could be a surface and they could be subsurface problems. Okay, they could have problems like in the case of subsurface issue, we have in some cases what we call it ion exchange. You know, ion exchange, which leads to precipitations of unwanted material. Okay, so if you have, let's say, a salt in my reservoir, such as calcium or magnesium ions, and I inject water with another calcium and magnesium ions, I could have a problem or the ion exchange, and therefore we will have the precipitations. So we call this process is a scale buildup, which a scale buildup causes something called formation damage. In other words, like we have calcium and magnesium are building up in the reservoirs, and they are reducing or deforming the original permeability in the reservoir, so introducing formation damage. Um, Generally, it might not be that big issue, but you need, to keep it in your mind, because that's something you might need to understand if you want to analyze the productivity index of like the field or of the well for a long period of time, and this could be pretty much reason for reducing the productivity index. In fact, the best water that could be injected, that hopefully will not harm the reservoir, is the low saline water. And when I say like low saline water, that means they less than 10,000 ppm. So the fresh the water, the better for sweeping and the less for damaging. If you have fresh water, that means you are reducing the percentage of harming the reservoir, and therefore you will increase the sweeping efficiency. Another problems that's really common in water injection is the corrosion. Okay, which is like the big issue, especially if you have if you inject like a salty water. And I'm afraid that the production string, like tubing, casing at the wellhead, that even like service facilities, they will they might be corroded. And I have been experiencing many times that we have leaks in our pipes and service facilities, even though like we inject corrosion inhibitors. But sometimes no matter how much you inject corrosion inhibitors, not enough to prevent that leakage. So you have to consider the corrosion that might occur once you inject a salty water. And another thing, of course, if you have H2S dissolved in the water, so you have acidic, you have acid, salt, and high temperature, these together will cause corrosion and will damage the equipment and make it like very weak. So for the corrosion and, to prevent the problems like formation damage and the corrosion, you have to make sure that the injected fluid, injected water must be compatible with the fluid inside the formation, and it should be as much as possible to be fresh water. I mean, with a low saline is the best scenario that you can avoid harming the reservoir. Here we have the main water flooding stages, to check like when exactly we need to think about water flooding, and also what are the periods that like any water flooding project will pass through. At first, we have the end of primary depletion. When the natural energy is not enough to provide the sufficient pressure to keep, producing at the desired rate. So that's what we call the end of primary recovery. Obviously, like when water injection equals or exceeds the production measurement at reservoir conditions, the average reservoir pressure, is maintained. I mean, logically is maintained or even increased as needed. In those examples, primary depletion stops because, the predominant drive mechanism, like whatever you have drive mechanism, let's say water influx or any other drive mechanism, are a result of declining reservoir pressure. So once your drive mechanism is not sufficient or causing a decline in the reservoir pressure, so that's what we call the end of primary depletion. So during the time of constant or increasing the reservoir pressure due to water injection, the oil recovery is a result of displacement process. So you have to figure out the produced oil as a result of which part. We have two things. We have oil is being produced because of water injection, and we have a depletion in the pressure. So in the areas where we have an injection is less than the production, and where the average reservoir pressure is only partially maintained, so we have a depletion. So the reservoir, experiences a combination of two things, as I told you, a pressure depletion and the fluid displacement. But when both recovery process, like if you have two main things, the pressure depletion and the fluid displacement happens together, that means the reservoir behavior is like very complex and must be analyzed using numerical simulation models. So you don't need that happening by making sure that the displacement that the whole field is producing because of the fluid displacement. And how can you make that? You have to have like key wells in your field, and these key wells must be monitored, I don't know, monthly or weekly. It depends on the policy of that company. And you have to make sure that the reservoir pressure is maintained at the desired pressure, and try to avoid that in some areas the reservoir pressure is good while other areas the reservoir pressure is not good. So in that situations, you will make it very difficult to monitor the performance of water flooding just by conventional methods. So let's move on to the second period, which is the fill-up period. This period begins with the initial water injection and lasts until the first response in the production increase is noted. So in this period, free gas, if you have a free gas, it will be like displaced. If you have a trapped gas, it will be brought into solutions, and of course the reservoir pressure is restored. So it has been said that generally speaking, this period ranges from like 5% to 11% of the total flood life. That's actually depends on the heterogeneity of the reservoir. It depends on the flooding pattern, or depends on the well spacing and a volume that you are displacing, the voidage that you are displacing, all these things. So in general, the more heterogeneous, the layered the system, of course, you'll have the faster gas collapse, and you'll have a very short fill-up periods, which leads to like low peak oil rates during the production incline periods. And that might be an indicative of the channeling or bypassing, or possibly you have low levels of the pressure depletions. And of course, they can be diagnosed by many charts and diagnostic techniques, as we will see once we go further in this presentation. So let's move on to the second one, which is, or to the third period, which is the production incline period. This period occurs when the oil production begins to increase through the peak to the production rate. So we have, the production rate steadily increases, but we shouldn't have water cut increment. I mean, there shouldn't be a significant increment of water in production in this period. And the length of this period requires about more or less about 20% of the total flood life. And then we come to the most important period, which is the plateau period. This period lasts while like oil and water production rates are stable and ends when the oil rate declines, like while water rate increases rapidly. And this period depends largely on the reservoir homogeneity, depends on the interwell connectivities, it depends on the oil-water mobility ratio. So if the peak oil responses is weak or even non-existent, so that reservoir continuity or reservoir communications might be at issue. So usually the lack of water production at later times combined with poor gas collapse, so this is they might be confirmed by the charts of gas oil ratio and water oil ratio, as we will see it in the well level. Then we go quickly to the production decline period. This period begins after the peak rate has occurred. I mean, we reached the peak and we stayed at the peak point, and it continues until the limiting economic rate is reached. Like in most cases, the production rate decreases as water cut increases. And this is the typical and the logical thing. And this period, constitutes the largest percentage of the total flood life. I mean, it represents about 70% of the total flood life. And in general, the more heterogeneous, I mean, the layered the system, if you have, the faster gas will collapse, and you will have a short fill-up periods, and therefore you will have a low peak oil rates might be an indicative of channeling or you're leaving oil behind. So that's briefly was the main theoretical things that you should probably know before you start working practically on analyzing the performance of water flooding. In fact, after reviewing like many water flooding case studies, a key lesson learned about water flooding monitoring and surveillance is that to use methodological approach. And that actually starts from the large scale and then proceeding to a smaller scale, like starting from the field level and then moves to the pattern level and end up with the well level. And this methodology identifies, general opportunities and the problems that you have. Like as the analysis proceeds, it becomes more specific with respect to the scale of individual wells. And, of course, you can identify the problems and suggest the better solutions. So starting from the field level, surveillance provides baseline that can help differentiate like between poor performance and good performance. So that's why we need to understand the field level in general. Surveillance of individual wells, of course, is an excellent way actually to develop the if you want to make well specific recommendations after you understand the reservoir flow patterns. So that's why you understand the general performance with the field level, but the recommendations will be given based on each specific well. I mean, you have to analyze each specific well in particular well so that you can give, of course, recommendations. Here we have, as you can see here in this chart, a review of always like a review of production and injection history using plots can be very useful in diagnosing field response. It's the usual starting point of understanding how the field was developed, and of course you can identify what are the main problems in the production once you plot the production and injection history. So the charts you see in the production history, like these are the real data, and the production, as you can see here, the red line is for oil rate, and the blue line or the light blue is for water production rate, and the dark line is the injected rate or injected injected water rate. As you may notice here, let's get through the main points. The production, started from December 2006, and after about 1 year, the oil rate reached about 18,000 barrel per day. And the water, you can see it's like negligible amount of water with, and I remember that was the contributions of about 16 wells. Then the pressure declined immediately just after the production startup. So as you can see here, so it was decided to inject water to maintain the reservoir pressure. And the injection started at March 2008 with, the injection rate about 10,000 barrels per day. So the effect of injected water could be seen after like about 3 months of injection, and the pressure maintained about 1,200 psi. And then after that, more wells, were drilled, and the production increased up to 25,000 barrels per day, and almost there is no water production, and the injection rate was about almost the same as production, which was about 20,000 barrels per day of water injection. And then there was the first conflict, and the field needed to be shut down in 2011. And then after that, once the production resumed, the injection was not started immediately to avoid excessive water production, and the field, was closed for the second time, and it was longer time. You are talking about, about 40 months. So analyzing the pressure for the field life might not be that easy thing, or might not be that useful, and in many cases might be tricky, because like you have a huge variation in the reservoir in the pressure points at the same period of time, as you can see here. And now, I want you to figure out why these variance in the reservoir pressure of a single field. This is a single field, but the reservoir pressure at the same time was not given. I mean, there was more than 400 psi, the difference. So if you take a deep look, you will find out that in the shut-in period, the whole field acted the same. So we come up with the conclusion that statically, the field is in communications, because once we close the field, when the field is shut in period, we have narrowing in the reservoir pressure, and they are all acting the same. As you see here, the big variation starts to decrease until we reach almost the same reservoir pressure. Okay. So statically, the reservoir was in communications, and there are no faults preventing the aerial communications. However, and the pressure support is not acting the same along the structure. I mean, dynamically, they're not acting the same. So, pardon for this thing. So they are not acting the same. So that's why we have, once we start production, we have a big variation in the reservoir pressure according to the aquifer strength and the pressure support in some areas, while statically we have the same. So that's important to analyze the history and production plots before you start injection. Here we have the voidage replacement ratio. Actually, voidage replacement ratio, or VRR calculation, here we have it for the whole or the entire field. VRR, what is VRR, by the way? VRR is defined as the total fluid volume injected and divided by total volume of fluids, produced. You have a volume of injection divided by volume of production, and both, at reservoir conditions. Ideally, VRR should be approximately 1, equals to 1. If you have no source of energy, so you need, the amount that you produce it must be equal the amount that you injected. But in some situations, you have high VRR values, which might indicate that in situations in which what we call it over injection. Over-injection, can be, caused by thief zones taking injected water, or we have high permeability layers causing preferential flow if you have high permeable layers, and also if you have like fractured reservoirs causing, the direct cycling of water between the injection and producing, as we have seen in the previous slides. In the fracture part, the water was taken the easier path, the fracture path from injector directly to the producer, and you don't want that happens because you are actually over injecting, and that will lead you to early production or early water breakthrough. On the other hand, if you have like low VRR values, indicate in situations in the produced fluids are withdrawal faster than the reservoir per volume is being filled, with injected fluid. So this results in the pressure drawdown and increases the free gas saturation, forming the reservoir, which is like undesirable thing. Here we have in this chart, this is the real data and the VRR calculations, okay? The optimum VRR that maintained the optimum reservoir pressure, it was found to be 0.6. But always remember that this is only a field level. And as you can see here there is a big variations in the pressure points. So this VRR shouldn't be a representative for the whole field, because in some areas we have good reservoir pressure. We don't actually want to inject water, while in other areas the reservoir pressure declines very sharp. So they might have a VRR maybe more than 0.6. It might be like 0.7 or 0.8, because we have to introduce more energy to the reservoir. Let's move on to another diagnostic plot. It's an interesting thing called the conformance plot. Actually, conformance plot indicates how efficiently net water injection affects the reservoir oil recovery. And you actually are comparing the net water injection with the resulting of oil production that enhanced, the understanding if you have influx or efflux to the fluids, as well as the losses of water to non-pay zones. So conformance plots are, specifically helpful for the water floods due to the two main things. I mean, you have low compressibility of oil and water. That makes the conformance plot really helpful. So if we plot the oil recovery and net water over the movable per volume, you will end up with this chart. Okay, and the graph should have like 3 options. If you have a straight line, that means you are, this is like an ideal case, and there is like you don't have any influx or efflux in this situation. However, if you have any change in the slope in the conformance plot, I'm sorry for this one. So if you have any change in the slope of conformance plot, that may indicate may indicate an efflux. That means you have the curvature goes a downward curvature. That means you inject water, You increase the volume of water is injected, but there is no big increment in the oil recovery. In this case, that means the injected water goes to the thief zones, and we don't actually get the use of that injected water. So you have to make sure that the injection water is going into the right direction. So if you have the downward curvature, that means there are thief zones or unwanted layer or unimportant layer, and the water goes to that layers because it found it easy path to go in that direction. However, if you have an upward curvature, that means we don't increase. That means there is another thing enhances the water production to increase the recovery, because we have a small increment of water injection and higher increment in the oil efficiency. That means there is another fluid that enhances the sweeping efficiency, that increasing the oil recovery. So that's why analyzing the field level performance can tell you, if you are going in the right direction or not. And this is the real data of one of the fields in North Africa. Okay, and if you plot like the recovery factor against the water injection rate, which can be calculated as shown in this formula, we will have this like plot where the recovery increases as net water injection increases until we reach like a deviation in the slope, what we call it breakover point. So what is breakover point? The breakover point actually occurs at a time when we have bypassing starts. When you start bypassing, when you are leaving oil, so that's the breakover point. And normally for water flooding, performing well, the breakover point, occurs at approximately, let's say, 20% of the total oil recovery. And that's is assumed to be under favorable mobility ratio. But, if you have early breakover points, as it is the case in our example here, that may indicate that you have heterogeneity or unfavorable mobility ratios. So in general, projects that exhibit early water breakthrough due to extreme permeability variations. So if you have the later breakover point, that means the better for sweeping efficiency performance. Okay. So that's actually what I want to talk about. So that's basically about the field level. And now it's time to go to the pattern level. Analysis at pattern level helps to evaluate the regional volume balance. And of course, they represent the most difficult part of the water flood management process. Always, correct analysis requires that you need to identify injector-producer pairs, like what are the most pairs that suits your reservoir. And you remember the field level analysis, the key performance indicator for the patterns is the voidage replacement ratio. And actually we will do the same for the pattern level. As you can see here, this is a field consists of 41 wells, 25 producers and about 16 injectors, and arranged in 8 inverted 5-spot patterns, which is like one, you have one injector and surrounded by 4 production wells. Okay, and they are assigned to each patterns according to their distance to the nearest injection, and this is normally the case. And we initialize the geometric allocations factors upon because of the distance between the injectors and the producers. For water flooding, the most common pattern of injection and production wells is 5-spot configurations, as you see here in this field. where I have like one injector in the middle and I have 4 producers in the corners. And this is like normally the typical situations. But of course, there are like many other patterns, such as 4 spots. You might have 7 spots, even 9 spots. You might have like scattered one, and you might have the line to line, one producer and one injector, or you might have the peripheral one. That means you have injectors surrounding your fields, and then this ring getting closer and getting narrowing to the field until you produce all, not all, like let's say 30%, 35%, as this is the most optimistic covering um, percentage. So this brings us to think about what's the ideal pattern. I mean, how can we decide which pattern do we need to use in our field? Actually, there are many parameters that we need to consider. The first one is to like promote the faster oil production response. Okay, and we should always think about establishing the project with minimum number of new wells, either for production or for injection, and reaching the desired oil rate and the injection water rate. And we have to ensure the maximum volumetric coverage of the reservoir slope and size. We have to accommodate the reservoir heterogeneity and anisotropy, as I told you. If there are any faults or any heterogeneity, you have to make sure that you are taking this in considerations. You have to minimize the water production as much as possible. Of course, the water it will be produced sooner or later, but try to make it later, not sooner. Most of the time, like, it's impossible to meet all these requirements because the field might be already developed under different considerations. They might be like irregular well spacing during the primary. But as I told you, monitoring and analyzing the performance, either from the field level or well level, helps you to monitor the process. So here are the main patterns that were used in our analysis. And this is the production data and the pressure history and the VRR for that specific region, the red one here. We have the production and the injection figures of this exactly this area. And the injection started after a year of the beginning of production, and during that year the pressure decreased to 1,200 psi, and of course it will decrease more if you didn't start injection. So that's why we started water flooding. And like, if you have noticed that the pressure points were smooth, and that because they have the same pressure support along this pattern. So that's why we need to understand the drive mechanism, and we need to understand the how to make the patterns that they are actually acting the same, because they will be displaced in the same manner. And the target reservoir pressure in that field was about 1,200 psi, and the corresponding VRR that maintained this reservoir pressure was 0.5. So that VRR was chosen to be the optimum VRR that maintained the reservoir pressure, the desired reservoir pressure that I asked it or that I wanted to be at. And like, what does it mean if you have the VRR 0.5? Actually, that means the water flooding gives us 50% of the support to maintain the reservoir pressure. And the other 50, comes from other source of energy. In our case, we have water influx. And this is actually, we don't need to have a VRR 1 or high numbers like 0.9 or 0.8, because we have a water influx and we could maintain the reservoir pressure with only 0.5. And here we have, like if you remember the conformance plot, the same idea, we will apply it for a specific pattern. And as you can see here, at first we have a straight line, then we have an upward curvature, which indicates that an influx in addition to the water flooding, which proves the idea, or like the previous slide that says that there is a water in addition of water flooding. So once you finish, or once you analyze the water, the field level, and then go to the pattern level, now it's time to go to the well level. Water flooding analysis in the well level is essential, especially if you have to assess the health of individual producer and injectors. So we were talking somehow general. Now we will talk a bit of, specifically. Let's start with something called Heterogeneity Index. So what is Heterogeneity Index? Actually, it's a process of, quantifying the well behavior dispersion, comparing actually one individual well to the average of the group of wells according to the formula that you have. So let's say you have this value of a specific well. You have the oil rate of a specific well, and this is, you have the oil rate, the average oil rate of, of the whole pattern or the whole field. Okay, so, and then you can subtract it by 1 to normalize the heterogeneity index to 0 to calculate one of the 3 conditions. Okay, you will have 3 scenarios. The well performance, like matching the average rate, let's say, or the average value, the heterogeneity index will be 0. If this well is matching the average, like equals to 1 minus to 1, it will be 0. So the heterogeneity of that well means is the dispersion in that well is very, very low. Another scenario, when you have the wells that performing above average, they will have a heterogeneity index value greater than 0. And the opposite, if the wells performing below the average, they will have the heterogeneity index less than 0. So we usually take the help of a scattered plot of X and Y coordinates that can be used to identify the locations of the problem wells in the field. From that plot, you can recognize your wells. So the location of the wells that are performing good, which they represents in like high oil and low water. For example, here we have this chart. If you have, this is for heterogeneity index for oil, and this is for water cut. These wells are performing high oil and low water, and these wells high oil and high water, while these wells low oil and high water, which is the worst case, and this is for low oil and low water. So you can actually identify the locations of the problematic wells, the wells that you have problem in. So you can identify their locations, and now it's time to know why do we have problems in these wells. So that's, brings us to Chan graph or Chan diagnostic plot. Actually, in 1995, Mr. Chan proposed a technique to determine excessive water production mechanisms. And that the beauty of it, that was based on the results of simulation studies. And it was observed that the shape of water-oil ratio versus time, they could differentiate between, water production due to coning or channeling. First of all, what does that mean if you have channeling or fingering? That means you have created a conductive path between producer, or between the injector and the producer. Okay, and coning, of course, all of us know what that cones mean. Coning means the water is going, the free water level is getting increased, and the water approaches the lower perforations, and then the water starts producing from the lower perforation and increases as we increase the production. So we can use channel diagnostic plots to differentiate between channeling and, of course, coning. To do that, we have, we have to divide the periods of channel plots into three main periods. The first period is like prior to water breakthrough. I mean, there is no water production or dry oil is being produced. So there will be a straight line, a constant ratio in the case of two-phase production. And there is no water breakthrough yet, like this one. We have a straight line and we don't have any water breakthrough in this period. And then as we proceed and as we produce more oil, and we reach to the period of, we name it earlier period after breakthrough. So once we reach the breakthrough, we have two other periods, earlier period and later period. If the earlier period of after breakthrough in coning, as you can see here in this one, the water air ratio increases slowly and like gradually and approaches like a constant value at first. You can see here the increment is somehow gradually. But for water channeling, the water ratio increases rapidly with a water breakthrough in the higher horizontal permeability layer. It increases at constant rate until the next higher horizontal layer breakthrough. So that's makes it like a stepwise behavior is usually observed in the water channeling. And then as we move on to the later period after breakthrough, for coning, the water ratio increases like rapidly. I mean, this is the opposite. Why? Because the water cone becomes highly conductive channel. But for channeling, the water ratio increases with a constant slope, even if with the later period, with the constant slope, and as that determined by the relative permeability relationship. So the distinction between the water channeling and water coning actually becomes more apparent if we use the derivative of the water air ratio versus time. Like for coning and channel for coning, we have a negative slope is observed. Here we have the derivative, a negative slope of the derivative for coning. While in channeling, we have a constant positive slope is being observed in water channeling. So that's how we can understand the source of water. I mean, where does it come from if we have channeling or we have coning? However, this is only like a diagnostic plot. We cannot judge based on only the diagnostic chart, like Chan plot. There must be other means that proves our idea and that helps us think about detecting our problem like exactly. For example, we should have a PLT that can tell us the contribution of each layer and like the water percentage if for each specific layer, so we can make sure together we can have a big or a good picture of the source of water. Here we have an example of a real data, and at first we have a straight line, before the water breakthrough, and then the water air ratio increased and took a stepwise shape, as I told you, which is an indication of water channeling. Of course, like you cannot, as I told you, judge based on just a diagnostic plot, but as you can see here, we have a straight line and then at first increased rapidly, very fast, then took a stepwise And this stepwise shape as an indication of a channeling. And of course, if you have a channeling, is more complicated problem than coning, because if you have coning, you might think of isolating the lower perforation or the water that produces the layers or formation that produces water. But for channeling, you might need to reduce or choke back your producer. You might need to just uh, reduce the water injection or reduce the VRR, as I told you before. But this is not exactly the main aim of this presentation. But here we diagnose the source of water. We came here to the last slide in this webinar, which is the whole diagnostic plot. And the whole diagnostic plot actually, it's really important maintaining the injectivity index of a well at the desired value. Why? To have like to make sure that you are delivering water to the formation. So a whole plot is actually a simple method to analyze the injectivity data to assess the reasons for any change. And of course, you should take the actions that must be taken to solve your problem. So the main aim of whole plot is to understand the health of your injector. So what is whole plot? Whole plot actually in 1963, Mr. Holt, presented a technique to analyze skin effects of injection wells. And the technique uses Darcy's law for like a single phase and takes all the assumptions of Darcy's law, like steady state, Newtonian flow of a well centered in the circular reservoirs, and assuming that you have constant permeability, constant thickness, constant viscosity, and all these things. So the plot is we have a weighted sum of the surface injection pressure versus times versus multiplied by times versus the cumulative water injection yields, a straight line. So the shape of the plot is indicative of the injection behavior of the well. For example, let's start one by one. If you have the red one, okay, you have a straight line at first, then we have an extreme upward curvature or a steep upward movement. That means no matter how much we inject the water, the wellhead pressure will increase rapidly. So it's like a small increment in the water injection, and the wellhead pressure increases a lot. So that means the injector or injection wells is not able to take more water. Okay, and this is suspected to be damaged. I mean, this is the general aspect, because the water is not accepting water, the formation is not accepting water, and in this case we might think that this injection is damaged. And what we do to the damaged wells, we need to stimulate the injector by doing fracturing or acidizing. It depends on the petrophysical properties and depends on the mineralogy of your formations, and we need to stimulate that well. And another case or another line, if you have the second one, the green dashed line, is you have a gradual plugging well. This is most likely the most common cases. As I told you, because of injecting water with high salinity, you will have a scale buildup in your well pore. So you might need to do like acid wash to remove that scale buildup and to increase the injectivity index of that well. And if you have the third line, which is the typical and the ideal case, once you increase injection, the wellhead pressure increases. So you have no change, there is no plugging, there's no damage, and the formation works properly and takes all the water that's being injected in the proper way. And the fourth one, we have first we have a straight line until we reach to a point, then the water in the cumulative water injection, or the injected water, increases very fast with the same wellhead pressure. That means the wellhead pressure we don't need to increase wellhead pressure to take more water. And that's actually an as indicative of stimulated well or a sudden channeling. So in some situations, we inject water above fracture pressure. So we open a new channel, we open a conductive layer, we increase the permeability of that specific layer. So that formation, takes all the water that we inject. So generally, this can tell you, if you plot the wellhead pressure. Actually, by the ways, you can plot the wellhead pressure versus the injection rate, or you can plot the cumulative water with wellhead pressure multiplied by time. So both can give the same results. And of course, like if you don't have that big history, you can just plot the injection rate versus the wellhead pressure, and you can have an idea about the status of your injection. So I'm sorry for being too long. It's about like 1 hour and 10 minutes. Thank you so much for your attention and for being patient. I'm glad to hear all your questions and your feedback. Thank you so much.
Thank you so much, Mr. Grada. Thank you so much for your hard work. And we learned so much from this interesting topic, the water flooding. And we have here some questions in the chat box. If you want, I will read it for you. Or we have here the first question. Well, is the rock fluid interaction to take in consideration in water flooding? This is the first question. And we have too much questions, so we start one by one.
Okay, I would prefer to like start them one by one. Let me open
Yeah.
the chat box. Okay, I'm here.
Okay. The question in the chat box, you can read it, and I can read it for you, or you can read it as you want.
Okay, I would prefer like reading by myself to understand the
Okay.
question while I'm reading it.
Okay.
Okay.
Thank you so much again.
You're welcome.
Well, guys, now we will pass to answering about the question. If you have any question, just write it in the chat box, and here Mr. Grada to answer you. Thank you so much.
Here we have the first question. Says that, is the rock fluid interaction to take in considerations in the water flooding? Well, like in reality, we don't actually spend too much money to the injected water, because what matters, I mean, for the management perspective, what matters is the produced oil. But like for a long vision, it's important to know about the injected water, and we should have specific qualifications for the injected water to avoid any problems while we are injecting water. One of the tests that we have to do is the compatibility test between two fluids, the injected water and the water that exists in the reservoir. Another test that could be done, which is says that if there is any additives that will is being added to the injected water, of course they should have test the interaction between the injected fluid and the fluid inside. But reaction between fluid and water, the rock and fluid, there shouldn't be any reactions. I mean, in addition to the compatibility, we are not actually talking about acidizing or chemical reactions. We are just talking about physical displacement. If you are talking about acidizing reactions, or of course I told you about the ion exchange, and this is depends on the compatibility test between fluid and fluid. I mean, it's not between rock and fluid. If you're talking between rock and fluid, that's somehow that requires chemical reactions, and this is it shouldn't. I mean, it's not that important to take in considerations in the water flooding. I'm not sure if that was the answer that you seek. Let's move on to the second one. If the reservoir pressure is at the bubble point pressure, okay, should we inject with a VRR higher than 1? Well, if you are injecting, I mean, let's make it really simple. The VRR is tells us the amount of water injection that we need to inject because we produce a specific amount of liquid. Okay, so if you want to maintain the reservoir pressure and you have no other source of energy, you have no water influx, you have no any other source of energy, and you want to maintain the same reservoir pressure, it must be equals to 1. And if you want to increase the reservoir energy, I would say you might need to if you want to increase, I mean, you want to build up the reservoir pressure, you might need to think about increasing the amount of injected water. But you can increase the reservoir pressure, but the water production might be or might take a place earlier than it should be. So that might be an issue. But of course, it depends on the policy of that company. For example, in some companies, they don't allow to, you have like a specific, how to say, a specific oil rates that you cannot, exceed because of many things, because of the service facilities and because of other limitations. But if you solve all the limitations that you have, I guess you can do both water flooding and water injection at the same time. So that's of course will lead to increase the VRR above 1. Another question is the simulation sufficient to choose the optimal local for the injection wells? Is the simulation sufficient to choose the optimal local for injection wells? Well, of course, simulation modeling helps a lot to predict many scenarios, and you can try many cases as much as possible to end up with the best recoverable case. And this actually requires a good set of data, and you have to be in a certain level of your field life. I mean, you cannot do that in the first field life, even though you do it, but it's not actually a representative thing. So of course, simulation can help you a lot to make the optimum optimum injection wells. Okay, go to the second one. I have some questions. Should we consider? Okay, thank you, Mr. Ali. Should we consider the reservoir size, because some fields width are more than 5 kilometers, and we can inject water. Compatible with existing. When can the injected water compatible with existing? How to prove that? Okay, and the last, it sounds there are many questions. Have to avoid corrosions, and what's the best collector type to flood pure water? Could you explain the question very fast? Of course, you have understanding the reservoir with the reservoir size is really important, And it's critical to know, I mean, even with a qualitative knowledge, I mean, it's not necessary to be like specifically the number. Why? Because you have the area, and there is something, actually I didn't put it here in this presentation, but maybe in other sessions, which is it tells you like the injected water, how much does it need, the time to reach, like to cover the whole field. Sometimes you have a very small field and you don't need to inject a huge amount of water. On the other hand, you have a big field and it takes you like years to cover the depends on the policy of that company, and depends on the mentality. Like for example, and they want to produce very I mean as early as possible, while other companies they want to produce that oil and doing the sweeping efficiency very I mean in a long want to produce that oil. I mean, does it really matter to you to produce water and leave oil behind, or does or the I mean, does it really matter to you to produce an early water breakthrough or not? So that's the situation. Most likely in local companies, they actually care about water production. However, secondaries or surface companies, they're not actually want to focus too much on that thing. So this is different perspectives and different point of views. Of course, we can do compatible tests. Actually, I haven't done a compatible test before, but I would imagine that we can take a sample from water, produced water and the injected water, and mix them together and try to find out what are the reactions that may happen. So if there is any reactions, so that means, I mean, if there is a precipitations of unwanted material and there is ion exchange, that means you are, you know, they are not compatible. But if they're not, so they are compatible actually by taking samples. And this the thing, I guess. How to avoid corrosion? To avoid corrosion by two things. The first thing, we need to reduce the source of water by, you know, injecting fresh water. So if you inject fresh water, you are reducing the chance of, you know, corrosion. I mean, with less salty water. Another thing, if you have like a salt water and there's no way to inject fresh water, you might introduce inject corrosion inhibitor. I mean, for the surface facilities, of course, not in the formation. Okay, so for the surface facility, you can inject a corrosion inhibitor, and with amount and the rate at the desired amount and rate that helps you to prevent that corrosion. What's the best collector type of pure water? I'm afraid I don't understand this particularly question. What's the best collector type? Um, oh, I'm sorry, I don't actually understand this one. Could you please explain the VRR clearly? The VRR is the ratio between injection and the liquid production, and it should be equal to 1 if there's no source of energy. I mean, if you want to inject the amount of water that you are producing it to maintain the reservoir pressure, so the VRR should equal to 1. But in some situations that in your field, you have aquifer support, but this aquifer support is not enough to maintain the reservoir pressure. What do we know? What do we need? We need to introduce other fluid, let's say water injection. And the water injection is like how much water injection we need to maintain this reservoir pressure. And this is actually decides like how much exactly the amount of water. So if the VRR equals to 1, that means we don't have any source of energy. If VRR equals to, let's say, 0.5, that means 50% comes from the reservoir, the natural energy, and the other 50, the one that I introduced it to the by water injection. So this is the VRR. Okay, and on page 16, why did you shut down the field many times? Well, actually, we didn't do that. I mean, intentionally, because of the conflict that happened to my country and to the field. So we needed to close and shut in the field for all this period. It sounds weird, like in some countries, but this is actually what happens. That's a good question, by the way. Okay, during the injection area, there any chances that the injected fluid leaked off to other zones instead of production well? In that case, how should you proceed? Yes, as I told you, for conformance plot in the field level or in the pattern level, tells you whether you have going the path of injected water going to the right direction, or there is another fluid coming to the or supporting the recovery, or the third option, which is your example here, going to the thief zones. If you plot confirms the plot and you have you confirmed that there is like thief zones, you might need to do some techniques that prevents that path. For example, I remember that in some fields they did like a polymer gel, and they closed the fractures that that leads to the thief zones. Okay, so they actually isolated and plugged these layers. Another thing is to choke back your injector to try to restore I mean try to reduce the amount of injection the amount of produced water, but generally speaking it's not an easy task to I mean to redirect the water, because it has been it already found the way from injector to producer. So that's the thing. But I would say that if you have let's say thief zones, you should detect these thief zones. I mean, in which areas, and you might need to change the production rate, and of course you need to change the water rate, and of course you can isolate the water that the formation that produces water. So it depends on specific situations, but like nobody can tells you what can we do to the thief zones specifically. And actually this is by the analysis of well level specifically you can give the best recommendations. Okay, how can the waterability of the reservoir affect the flooding efficiency? Well, this is actually very good questions. The wettability actually, what is wettability? Wettability is the permeability over the viscosity. And what we are looking for is reducing this is the not the mobility. I'm sorry for that. This is the wettability. Yeah. Yes, actually, I don't actually have the right answer for this question, but it's really important one. I would review and I will come back to you, Mr. Mumin Hamama, and I will have an answer for you. For now, I don't have a very good answer, actually. I will need to review it, but it's really a good question. And I have some thoughts about this one. Okay, we come back to the last one. Is there bracket levers laws are used to water flooding or water injection? Actually, no. I didn't use them before, and as I told you, Mr. Monem, yes, Mr. Monem. So I will try to analyze. I will try to review my lecture, and I'd come back to you with the quiz questions. Thank you a lot. I think this is all, and it's been a quite time, 1 hour and a half. Thank you so much, and please, if you have any comments or feedback, please share them to me, so we can talk together. And of course, I would love to hear your thoughts, and of course, I'd like to hear your piece of information and whatever you can add to my knowledge. That will be really welcome. Thank you so much.
Thank you so much, Mr. Gada. Really, we learned so too much from you. Thank you so much. I think all the questions are done. Do you want to add anything, or we just finish the session? I think, I don't know. I think no questions. No questions. So guys, so thank you so much, Mr. Gad, again. You did a great job and we learned so much from you. Thank you so much again. And thank you guys to joining us. Uh, we will finish our session now. And please be safe and see you in another session. So goodbye and take care and be safe.